In this video, I will be demonstrating how a differential arrangement pencil probe can help minimize the effect of gradual effects, such as thinning. Now, I'm not saying that thinning material isn't important, but if you were more concerned with cracks than with thinning, this would be a good probe. Now, this particular differential probe has a line on the left side of it here, and you have to keep that line facing the direction of the probe travel if you want to find your short, tight cracks. And this is a very tiny tip, maybe a couple millimeters across. That's because I'm looking for small cracks. If I were to use a conductivity probe, I would have no luck finding the tiny cracks. So coil diameter is very important. It's actually almost more important than your test frequency, because you can use a big wide coil and run a super high frequency to try to get that skin effect and be sensitive at the surface, but it's not gonna work, sorry to tell you. So I'm gonna take this thinning wedge, I'm gonna put my differential probe on the thick end, I'm gonna scan down the material, and I have my alarm set. So if I pass any cracks, we're gonna get a loud noise. I'm gonna null my coil, my instrument. Now I'm scanning down the thinning material, and notice how my null point doesn't move. That's because the coil is so small, it's only a couple of millimeters across, that anytime the coils see the same thing, I got close to the edge though, so I did that. Anytime the coil's field of view is the same for both coils, the impedance point isn't gonna move that much. Now when I go off the end, obviously it's gonna set the alarm off. So now I'm gonna take this simple aircraft aluminum cowl block. It's got some cracks on the left end here, and it's got a tiny crack in the radius. This simulates the wheel bead seat over here, maybe. And then we've got the holes in the middle. They have tiny cracks coming off of the edge. Then on this end of the, I can kind of catch the end of that crack with my fingernail right here. And then there's a couple cracks coming into the edge of these holes on the back. So I got to make sure that I'm holding the line in this probe in the direction of scanning, which I will do. Now, I don't have this radius of this polar alarm gate set up to catch the 8 mil deep crack. Here I'm going to null. So now I'm just going to, because I'm scanning an aircraft carries bombs and people. It's important that I find all the cracks. I'm actually going to assume that there's a crack in here, and I'm not going to stop till I find it. Okay, so I'm scanning back and forth, scanning back and forth. I'm not even looking at my test instrument. I'm looking at the surface of my material. Let me show you. For real, I'm not looking at the tester. I'm just making sure that my probe is normal to the surface. Maybe my box is a little bit too small. Hold on. I'm going to take a little bit of horizontal gain out. See if that helps us. Make sure I hold the probe in the direction of travel. No. You know, one other thing I got to do, if this demonstration is going to be worth a darn, I'm going to have to put a little delay on that persist. Maybe like that looks good. Now I'm gonna null, so that way my screen will clear. Okay, null, buddy. No. I gotta set it down to null it. Give me a break. Okay, that's null. So, scanning away, paying attention to my probe, making sure it's normal to the surface. Oh, I was getting close to a crack there, that's high. But see how the null point stays in the center of my screen? I'm just being intentional to hold my probe normal to the surface. But when you cross I'm going to cross the 20 mil deep crack. See? I could have made my circle a little bit smaller, because I want to catch that crack. And if I scan over it the right or the wrong way, it doesn't set my alarm off. So I got to shrink that polar plot alarm gate if I want to catch that one. But what if I'm just really after the big ones? The reason it's not great amplitude is because I'm holding my probe not correctly. I need to have the line on the probe facing the direction of travel. Now watch what happens to the amplitude when I'm holding the probe right. See, it gets bigger. Now you got me wanting to shrink the size of our polar plot because I feel like I'm not catching the small flaws. Let's do it like that. Now, I'm gonna have to renull. Okay. Now we're gonna find the real small stuff. So I gotta scan very carefully. Keep my probe normal to the surface. That means perpendicular. And if I pay close attention and I scan carefully, my alarm won't go off unless I cross a big enough crack anyways. See, it doesn't catch that small one there because of the size of my gate. But when I cross the 20 mil crack, sets it off. And when I cross the 40 mil crack, sets it off. But you're not going to miss that signal, right? Even Ray Charles wouldn't miss that. Now I'm going to set the block down, and I'm going to scan past the edge of these holes on the front. I'm going to scan past the side of the hole with no crack. No crack, no crack, no crack. Now I'm going to scan past the second side with no crack. Nothing on that side of the hole. Then there's nothing on this side of the hole. But now when I go past the side of the hole with a crack, look what happens. Beep. I'm gonna try that on the second one too, because I want to make sure that's a little bit bigger crack maybe. So first I'm gonna go past the side of the hole with no crack. Ready? Here we go. No crack there. I'm gonna go past the other side of the hole 90 degrees away with no crack, no crack, no crack. I'm gonna go past the third side of the hole with no crack. Look at my null point, not doing much. But now I'm gonna go scanning past the side of the hole with a crack. Voila. You're not gonna miss that one either. Now what about these cracks on the back side? Where are they? These are tiny. There's one right there at the bottom and there's one right there. Tiny cracks. So let me just get down to my material, start scanning around, and this time I'm just gonna go past the side of the hole. It's got the crack. There's that one. I'm gonna go past the other hole. There you go. Now, I was going to get real clever and show you that I could find the one in this radius right here. It's about the same size, length, and depth of the other cracks. But I'm telling you right now, this is not the right probe to try to find that flaw reliably. And I'll show you why. Because I'm looking at the crack, I can see right where it is. And no matter how I try to scan past that guy, I'm going to scan right over the top of that crack. And no matter how I hold, see, it's right there maybe. Did you see that? Let me see, where is it? I know right where the crack is, and I can't even get it to show up where the darn. So what you'd want to do for this particular flaw in this radius is get a probe that's contoured probably, and designed to fit in that radius. You know, many aircraft, they're going to have standard probes that have a model number that's specific to that aircraft, and specific probes will be for specific applications, like doing the leading edge of a wing, and they have different ones for doing the edges of turbine blades, and so on and so forth. So anyway, here you've learned that differential probe will minimize the effects of gradual variables like thinning, like it's doing right here. But when you have nice, short, tight cracks, it's going to see them no problem. Not only are they detected easily by the probe, but it's easy to set them up with alarm gates, and it's easy to see them on your screen. All right, I hope you enjoyed this video. Have a nice day.